Hello everyone. In this video, I'm gonna solve another example, a beam example, a bit more complicated compared to previous examples. And using this example, I'm gonna show you how we can use the visual work method and the application of safe and unsafe theorems. I'm gonna elaborate on these topics. Okay, let's assume that we are given this beam. You can see here, the section at the right side is a bit more stronger than the one at the left side. The plastic moment is 2 mp and here it's mp. First of all, when we want to solve a problem using plastic analysis and also visual work method as a tool, we need to assume one mechanism. This is the first part. And then we need to check the equilibrium equation, derive them, and check the internal actions using the equilibrium equation. These two are the basis of the unsafe theorem. And if it satisfies the yield condition all over the structure or beam, then it is our unique answer. But up to this point, it gives an upper bound value. Let's get started. Here, let's assume one mechanism. It might be obvious for you, but let's only assume that mechanism is something like this. We have one plastic hinge here, one plastic hinge at the center, one plastic hinge here. Okay. Based on compatibility equation, the formation will be something like this. This is the place of our force. Here it will be, the length will be L over 6. This is L over 2. Anyways, this is theta. Then because of symmetry, this will be also theta. The deformation here will be L theta over 3. When we have theta here, rotation of theta also here, then the total rotation at this plastic hinge will be 2 theta. Therefore, for external work, we have one external work and one internal work. They need to be equal each other because of energy conservation. External work is P multiplied by L theta over 3. Okay, and the internal work will be here for this hinge is mp theta, the dissipated energy in this hinge. In this hinge, because the plastic moment is 2 mp, the dissipated energy will be 2 mp theta. And here, the rotation is 2 theta, and the plastic hinge is also 2 mp. Therefore, it's 4 mp theta. These are our dissipated energy in the plastic hinge. We need to sum these values to find the total internal work. Then it will be 7 mp theta. By putting these two numbers equal to each other, we will get the P corresponding to this mechanism, the maximum P corresponding to this mechanism. It will be 21 mp over L. Having obtained this maximum force, we can find the internal actions also for this mechanism at this maximum force. Let's find them. Here, it will be 2 mp here. 1 MP here also. Then here we will have this force 21 MP over L also on this side. The reaction here can be easily obtained at this side. It's 3 MP divided by L over 2, which will be, okay, which, so this is 2 MP. Okay, this will be 4 MP divided by L over 2 will be 8 MP over L. For this side, the reaction will be, for example, let's assume it's R or something, will be 2 MP plus MP plus 21 MP over L, and as you know here, the distance, this length is L over 6 multiplied by L over 6. Then we need to divide this by the whole length, which is L over 2. 3 MP here and 3.5 here, then 6.5 MP divided by L over 2 will be 13 MP over L. We can also double check right now. 8 MP over L here, 13 MP over L here is equal to 21 MP over L. Therefore, we have obtained these numbers correctly. Now we can easily draw our moment diagram. Let's get us started. Here it's 2 MP. Then it has to go up. Also 2 MP. Then in fact, it has to come here. Then MP here. For this point, it will be the moment will be 2 minus 2 MP, okay, plus 8 MP over L multiplied by L over 2 plus L over 6. Okay, then for L over 6 here, minus 2 MP. Then it will be 10 MP over 3. As you can see here, it's at this point, which the maximum moment is MP. This is 3.3 MP, and it's greater than this, far greater than this number. And here also at the center, we expect that this is 2 MP, similar to this point. 2 MP. This point is 3 MP. This is MP. Okay. Up to now, let's summarize what we have done. We assumed one mechanism. Using that mechanism and the virtual work method, we obtained the force to yield that mechanism. And based on that force and internal actions, we found the moment diagram, internal actions, you can see here. So we have right now mechanism, we have our equilibrium, both of them are satisfied. Then using these equilibrium and also internal actions, we see that at this point, the yield condition has been violated. Therefore, it means that the true mechanism, let's assume that the correct number that this correct force, true mechanism corresponding to the true mechanism that this structure can withstand is Py, then definitely it is greater than, it is less than this force that we have obtained, 21 MP over L. This is what we called in the previous video we called it unsafe theory, because the value, for example, if we say that the capacity of this frame is 21 MP over L, we are on the unsafe side, it's not safe. Therefore, when we are assuming one mechanism, it definitely gives one upper bound value. Now, we can still use this diagram, these numbers that we have obtained. They are not wasted. It can give us some other valuable information. Let's see how. As you can see here, it's 10 MP over 3, the maximum moment here. Let's multiply all these numbers by the factor of 3 over 10. By the way, the moment, the maximum moment happens here, and we know that the plastic hinge has to be on the left side where the section is weaker. Okay. So let's assume that we multiply all these numbers by 3 over 10 in order to make this maximum moment equal to the plastic moment capacity of this section here. Therefore, in that case, we are not going to violate any condition, yield condition. Let's do it here. This will be 2 MP multiplied by 3 over 10, 0.6 MP. At this point, because we multiply by 3 over 10, the maximum moment will be MP, and here it will be 0.3 MP. Right now, we are not violating any, at any point, we are not violating the yield condition, and the corresponding P value, the load is 21 MP over L multiplied by this. Okay, as you can see here, we found and obtained another force based on the lower bound theorem. Right now, we have not violated the yield condition. The maximum moment here is MP. We have our equilibrium condition, so this one also holds. Only the point is we needed 2 hinges to turn this 3 hinges to turn this beam into a mechanism, but we are getting only 1 here. Therefore, we out of these 3 conditions, we have only 1. Let me write them down here for you in this way. Therefore, mechanism, again, equilibrium, and then yield. Out of these 3 conditions, we are getting these 2. Okay, but not this one. based on the safe theorem or lower bound theorem, this number, this p here, gives one lower bound value, and we are sure right now we are on the safe side. We are only having one plastic hinge, therefore it's not mechanism. We are on the safe side. Uh, Based on this, we can say that py, the correct mechanism, is based on a force greater than 6.3 multiplied by mp over L. So this side, this part was safe theorem, and this side here is, sorry, just a moment, it's unsafe theorem here. And here we have our safe theorem. Now let's assume a better approximation mechanism, and it's in fact one hinge here. Let's do this, and the other two hinges are this part at this point and at this point. Having obtained these two, let's solve it. Okay. This is our compatibility equation. We have one plastic hinge here, here, and here. Then if the rotation here is theta, the rotation here will be 2 theta, and this displacement here will be 2L theta over 3. Then again, the external work will be our external work will be P multiplied by, let's call it Py from now, because we are sure that this will be our true mechanism. Py multiplied by 2L theta over 3, and internal work. We have theta, 2 theta, and here it will be 3 theta, and the work here, internal work at this plastic hinge, will be 2 mp theta. Here it will be again 2 mp theta, because the plastic moment is 2 mp and the rotation is theta. Here it will be 3 mp theta. Okay. These are dissipated energy inside this plastic hinge. Therefore, the total internal work will be the summation of these three numbers here that you can see. It will be 7 mp theta. By putting these two equal to each other, then Py is equal to 7 mp multiplied by 3 over 2L, which will be 10.5 mp over L. As you can see here, this is somehow satisfying what we found from unsafe and safe theorem. If we find the internal actions and the moment, it will be almost a similar thing. It's not very hard. Then here it will be 2 mp negative, it goes up. For here it will be mp, half half of this and also negative MP here. 2 MP. Because we have only one load applied here, the moment changes linearly between these 2 points. When here we have one plastic hinge with 2 MP and MP, then it goes linearly between these two. We can be sure that it doesn't violate at some points. Right now we have our conditions. We have, let me write them down here for you. Mechanism, as you can see here, we have 3 plastic hinges. So definitely with this 3 plastic hinges, this beam turns into a mechanism. We are satisfying this equilibrium equation. Based on that, we found the internal actions, and it holds for all point of this. And also, having obtained the reactions, we can be sure that we are satisfying the yield condition. Therefore, this is the true mechanism, and it's our unique answer. That's it. This is the overall, overall thing about plastic analysis. I'm gonna talk about frames in next videos, and also more important thing is to use optimization method based on Safe theorem and find the maximum force and solve this problem much more easier. I'm going to show this in next videos. I hope you subscribe and follow my channel. Thanks a lot for your attention.